Hello. Today we're going to be talking about just general theory and algorithms, an overview, trying to talk about some of the greatest hits of this really large field. Um, we're assuming that you've already been exposed to data structures and some other general ideas, but we're going to, for the most part, just cover things from the beginning. So what we're going to be talking about overall is the importance and when to apply an algorithm or an algorithmic approach. One goal of what you should learn is some intuition, get some tools in your algorithmic toolkit and use those appropriately. We'll also highlight some of the big algorithmic approaches. There's greedy algorithms, there's divide and conquer, there's randomization as an approach to sort of shake things up, and there's dynamic programming. There's other sorts of algorithms that we're not going to have time to talk about today. We'll try to provide some supplementary material for people who want to go above and beyond, but really these approaches are a pretty good starting point. Really, the overall learning objective is we want you to be able to reason about how to algorithmically approach a novel problem. And you probably have some intuition for what an algorithm is, but really a good simple definition is just an algorithm is something that gives you a recipe step by step to try to solve some sort of problem. Get some input, or take some input and get some output. So just building your intuition about that and how to think that way when you face a problem. And we also want to call out some of the connections between algorithms and data structures. There's a reason that those are always said together. Algorithms have data structures beneath them that make them go, and in general, innovation and efficiency and research in algorithms is tied very much to the same thing in data structures and vice versa. So first, we're going to start by trying to motivate a little bit about Big O and why algorithms matter. Big O is a measure of runtime efficiency in an asymptotic sense. So what that means is it's a very coarse, rough measurement. Asymptotic means we're just assuming if you keep throwing data at it, what happens? And we don't care about what are called constant factors, which might be how many times we always run this 10 times at the beginning of our program. Well, we don't care about that. We care about the things that you run that grow as you throw more input at your program and measure the size of that input in. So here are some of the major classes of Big O. Big O of 1, which is called constant time, is, for instance, just literally pulling out a direct record that you know the offset of out of an array like this. And that, you can think of that as free. I mean, technically it costs something, and there are situations where you might even care about that cost. But generally speaking, when you're thinking algorithmically, something that's constant is free. It can happen. There's logarithmic, O of log n, and an intuition for this visually would be to think about a tree. So a tree has many more nodes than it has layers. This tree is only 3 layers deep, but it has a total of 7, but almost 8 nodes, which is 2 to the third. And if we added another layer below, it would be even double more nodes, et cetera, et cetera. And so you only have to, though, go 3 deep to get to the bottom of it, or 2 hops, really. So logarithmic grows as you add more nodes, but it grows very slowly. It doesn't take that many hops to get to the bottom of a tree, even if you add a whole lot of nodes. A good rule of thumb for logarithmic is log of almost anything you care about, it's 30 or less. I mean, not exactly, but it basically the human population fits in about 32 or 33 bits. So log does not grow very fast, and you're unlikely to encounter that many numbers beyond that unless you're doing something very specialized. Next up is linear. Linear is you get what you pay for. You see what you get. Every new thing is just added to the end in this visualization, and you can think of this as a linked list where you have to follow each link as you go to get to whatever next thing. And so there's just one more hop, one more cost of processing for each new thing. Linear is pretty scalable and is often sort of as good as it can get for any problem that logically requires you to actually at least look at every piece of input data once. In that case, linear is basically as good as you can do, and it can be pretty good. Now, log linear, you might see this one a lot. You might also hear it called linearithmic, but basically it's a linear term times a log term. And you can think of this as, again, our friendly list, but each part of the list has its own tree beneath it, and you're actually, for each thing in the list, are going down the tree. And as I said, log grows really slowly and is practically capped, around 30 or 40 for a lot of problems. So really, log linear is not much worse than linear. Something that's 30 or 40 times more expensive, that can matter. But generally speaking, it's not, it doesn't grow that much faster asymptotically. And again, that's what we care about here. And as we get to these bigger classes, you'll really see why. We've got n squared here. This is also called quadratic. And with quadratic, you've got a list, and each list is a list. Oh, all right. Well, you can probably already see, how would I actually look at each of these? Maybe a nested for loop. Oh, for each list of lists, for each list in the list of lists, for each thing in the inner list, do whatever. And indeed, nested loops are pretty much always going to at least be quadratic. And quadratic does not, it's not terrible. Modern computers can run quadratic algorithms up to a pretty hefty scale, but the scalability of it is a lot worse. So this plot gives an impression of the separation and how quickly it grows. When I talk about when I keep saying this word asymptotic, really what I'm meaning is you keep going more and more off to the right here on this chart. And the more data you throw at it versus the runtime, and they don't picture it here. You can imagine constant, that's just a flat line. That's basically the x-axis down here. Logarithmic, you can see, grows extremely slowly. Linear grows. Log linear, not that much worse. Quadratic, you start to see a bit of a curve here. Cubic, which I'll go back to show the picture of, but that's just like another nested loop that grows even dramatically faster. And exponential, which I'll talk about a little bit, is even crazier. And there's even things, you can do things that grow faster than exponential. We won't really talk about that because that's the realm of abstract theory that doesn't have a lot of practical application, but if you're interested, I'm happy to give resources. So this plot isn't even that big, but you can imagine if you could just visualize this plot growing out forever, the gap between log linear here and quadratic, it gets even bigger, right? Because this grows even faster as you get more data, and this continues growing, but much slower. And so all these things just keep growing apart. That's the intuition to think about here. So going back to this part, again, here is, cubic, n cubed, and you can see, okay, well, it's like a cube. It's a third dimension, and so we go like this, and like this, and like that. And you can imagine that actually you can keep on going to higher dimensions pretty arbitrarily. There really aren't any, at least practical algorithms, much higher than this. And you can't really visualize it, being the three-dimensional creatures we are. So we don't have that here. But you can certainly code it if you wanted to. And then last is a quick mention, exponential. So in this case, there's only 9 nodes in this graph, but what you really want to count, the calculation steps, are the edges here, these hops, and each node is connected to every single other one. It's like this fully connected sort of situation. And so it really explodes, as it were. Well, it's not quite every single other one, but it explodes as it continues. Each one is connected to more of them. So that's a visualization. You could also just think of it as, 2 to the x. That doubles each time. It grows faster and faster. And again, it grows very, very quickly like this. So what's the bottom line of all of this? Well, basically, an efficient algorithm can be the difference between something that runs and completes on computers you can pay for and potentially makes you money if it's a useful application, versus something that just explodes and can't be run even if you had a computer the size of the universe. So that's why we're talking about this. That's why this matters. Now let's talk a little bit about some different algorithmic approaches. One good algorithmic tool in your toolkit is what's called a greedy algorithm. And I'll talk about this in a moment. This is an example of one called Prim's algorithm. But first, let me just lay out a little bit about what a greedy algorithm actually is. Basically, a greedy algorithm is something where each step of the algorithm does one simple thing, satisfying what's called a greedy heuristic. What this means is it looks at some options that are immediately available to it and just picks one. Say it picks the smallest one based on some number. Now, then what does it do next? Well, it just iterates. It adds the next piece of data or whatever is appropriate for the problem. This will make more sense when we look at this particular example. And it just keeps doing that until it's gone through all the data. If the greedy algorithm is correct, then it gets the actual right answer to whatever your question was. Obviously, this is kind of a minimum for it to be an algorithm worth talking about. And then if you're lucky, the algorithm can actually be efficient. It can even be optimal. We won't worry about formal optimality proofs, but efficiency, again, just harkens back to big O. It will be, say, log linear, something along those lines, and that's not a bad place to be. This idea of a greedy algorithm or greedy heuristic is related to other terms you might have heard, like brute force, or perhaps a naive approach, a naive algorithm, because often the greedy heuristic, weird sounding term, but actually very natural. If you just try to intuitively come up with the first answer that you might think of for a problem, it might actually be a greedy heuristic that you came up with. And brute force just means apply it over and over again. So these are all related concepts if you hear these terms. Now the example we're going to discuss is called Prim's algorithm. And what Prim's algorithm does, pictured here, is it finds a minimum spanning tree for a weighted undirected graph. A graph is just a collection of vertices and then edges between them. It's weighted, which means the edges have some number that basically means their cost. And it's undirected because the edges are the same going from here to here. There's such a thing as directed graphs. Won't get into that right now. And a minimum spanning tree is just the collection of edges that span the vertices, which means connects all the vertices at minimum total cost if you add up the numbers associated with all the edges. And so if we think about this before we get to Prim, well, for one thing, okay, there'd be no point picking, say, this edge and this edge and this edge, because you don't need all three of these edges. They form what's called a loop. Clearly, you could drop any one of them and the total cost will be smaller. So, you can start thinking about that, okay. So what's a good way to actually solve this problem algorithmically? With prims, we start by choosing a vertex arbitrarily. In this example, it's down here, number 4, the source. Why arbitrarily? Why is that okay? Well, the output needs to connect all the vertices, so we can really start from anywhere because we know we're going to need to get everywhere. Then the next thing we do is we add the edges that we can consider next. This here, PQ in the pseudocode down here, refers to priority queue, which is a data structure that's efficient at finding the minimum. It happens to be a very natural thing for this problem. I might talk about it in more detail later, but for now, that's all you need to know about it. And we add both of these edges to the priority queue, and then as long as the priority queue is not empty, we try to say, okay, what's the cheapest edge in the priority queue, which again is something the priority queue is very good at telling us. And it says, oh, I've got 31 and 42. 31 is cheaper. Here you go. And then we say, okay, what does 31 connect us to? It connects us to this vertex here, 3. We haven't been connected to 3 yet. We just started with 4. That's all we've got. So we say, okay, let's add this to the set this is part of our answer, this edge here, 31. And let's add to the priority queue all the new edges that we can reach from this vertex that we just got to here. And then we just iterate, basically. So stepping through, okay, priority queue says, okay, I've got 19, 42, 51. Hey, 19 is the cheapest. Here you go. And then we say, okay, where does 19 take us? Takes us to 1. 1 is new to us. Let's take it. All right. And where can we go from 1? Okay, we can take this edge here or this edge here. Okay, great. Put those in the queue. Okay, queue, what's next? All right, this is the cheapest one. All right, let's add it. Does it? Well, let's check if it takes us somewhere new. It does. Let's add it. Great. Now what are the new edges to consider? Oh, well, just this edge. Okay, now we've got all the edges at this point in the priority queue. And you'll note that we're going to iterate and we're going to check every single edge. So already you can see, all right, we have to look at every single edge. That sounds like something that's kind of linear, doesn't it? So, and it turns out, by the way, that this priority queue is logarithmic in operation. So essentially, this is a log linear algorithm. A linear number of times we're doing something log linear. We're trying to get a minimum from a priority queue. But the next edge we add now, okay, well, 42. Oh, but wait a sec. We already have been to these. You know, this doesn't add any new vertex. So actually, let's skip this. Let's remove it from consideration entirely. So we remove it from the priority queue and we don't add it to the answer. All right, what's next? Okay, 51. Hey, that does connect us to something new. Let's keep it. All right, and then as a human, you're like, yay, we're done. We have a spanning tree. It connects everything. But as a computer, you've got to keep going till this condition is satisfied and we are done with our while loop. So we ask, okay, what's next? What's the next smallest thing in the queue? 75. Oh, well, that doesn't add anything new, so just toss it. What's next? 95. Oh, that doesn't add anything new, toss it. And now we're done. Now we've looked at everything. The priority queue is empty, and this is a minimum spanning tree. This is the smallest total sum of edges that you can pick that connects everything in this particular graph. And this algorithm works more generally. You can play through with other examples on the site and satisfy yourself, and you can look at the actual formal proofs if you wish. But for now, this is all I'll say on it. So what's next in our whirlwind tour of algorithmic approaches? Divide and conquer. What is divide and conquer? You might have heard the term. I mean, it's even an idiom, a way to refer to certain situations. But algorithmically, what it is it's a case where each step of the algorithm either solves a really small piece, what's called a base case, or it puts together two smaller solutions into one larger solution. And often this is coded up recursively. You look at a problem and you break it into smaller pieces recursively until you get to that base case. And then once you're at that base case, the solution's obvious and you sort of bubble back up putting that together. And this is also very naturally a log-in sort of situation. Logarithm comes up because you're often dividing the problem size in two as you go. Each sub-problem is half the size of the parent problem. And so you end up with a logarithmic sort of number of problems. The problems themselves, they might be linear to solve. And so again, you're in that log linear situation. Indeed, for sorting algorithms, and our example here is going to be merge sort, log linear is very common. It's actually the best you can do for what's called a comparison-based sort. A comparison-based sort is when you look at pairs of elements and compare, okay, is this element bigger or smaller than this other element? And that's the decision that you're using to sort. You might ask, well, what other sorts of sorts are there? More on that later. Certainly comparison sorts are the general powerful workhorse sort that you need to use, and it's what intuitively sorted means in most contexts. So how does divide and conquer apply to sort? Well, in the example of merge sort, let's think a second, what would a base case of sorting be? Well, the most trivial case is a single item. If you have a list or whatever ordered data set of a single thing, it's by definition sorted. It's the first thing, it's the last thing, it's the only thing. Great. So that's our base case. Now, how can we efficiently combine base cases? Well, if you have two sublists or that you know are each sorted, that's the convenient part. That's what makes this, we're not just combining arbitrary lists and sorting them. We're saying, okay, we're building up from subproblems that we know are already solved, starting with the base case. Then you can iterate over them linearly, comparing the first element of each and saying, okay, whichever one is smaller, that's the first element of the combined list, and then move to the next element of that list and compare it again and keep adding the smaller of the head of each list until you get to the end of both lists, and then you have a larger combined but still sorted list that you got linearly as you iterated over both lists. So let's step through how that actually works here. You can see we've got some unsorted data, and if we look at it, well, step through all of it. So what does this part mean? Well, first, this visualization skips the initial recursion because in a sense it just sort of happens. But we have all the items here, and what's going to happen is merge sort's going to split and look at the first half and then the second half, and then it's going to split and look at the first half and the second half, and it's going to keep doing that all the way down until it just looks at the basic individual items. And it says, okay, each individual item is sorted on its own, and now we want to combine them with their neighbors. So we want to sort this pair, 3 and 44. Well, hey, that's already sorted. So we just accept that 3 is smaller than 44, and indeed that combined list is still sorted. Now we have 38 and 5. Okay, well that's actually not sorted. So we put 5 first and then 38, and then they go back where they were. And then now you'll notice we don't go next to 15 and 47 here. What instead we're doing is we're sort of bubbling back out of the splitting down process that I described, and we're combining now this length 2 with this length 2. And we compare 3 and 5 because that's the head of each of these sub-lists, sub-problems that are already sorted. All right, well, 3 is smaller than 5, so we take 3. And then visualization doesn't exactly show it here, but we compare 5 with 44. And hey, 5 is smaller, so we keep 5. Then we compare 38 with 44, take 38, and then of course we have to take 44. And then this process just continues. So I'm not going to read every number as we go. We do it to the next pairs of items, and we combine those pairs of items into a list of 4. And now we have 2 sorted lists of size 4. So they get combined, again with the same process that iterates over each item of them. So, okay, we take the smallest one we can from whichever one, and going back and forth between them. I'll do that again one more time, slowly, because this is maybe a better example of a merge. 3 is smaller, 5 is smaller. Now we're on 38, but no, 15 is smaller, 26 is smaller, 36 is smaller. Now 38 is smaller, 44 is smaller, 47 is smaller. And there we go. And then I'll click fast for this part because it's just the same thing. And you'll notice there's actually an odd number of items here. That's not a problem for this algorithm. I won't go into detail why, but essentially all the same things work. It's still sorted on its own, and it can still merge in with other groups just fine. And then these merge together. And then now the big final merge. And there we go. And we have a sorted list. As an aside, there's lots of other sorting algorithms, and they're not all divide and conquer. Again, this was really meant to be an example of the divide and conquer paradigm. We take a large problem, divide it into smaller problems that we can solve, and then conquer, really combine, but yes, conquer, solve it. There's all sorts of others, and you can sort of watch them play out, and they have all sorts of, yes, generally the good ones are all log linear, but they have different behavior based on what the sort of data is, if it's already nearly sorted, if it's reversed, if there's not many unique things. The only other sort that I'm going to call out, though I won't explain in detail right now, is quicksort. And the reason I want to call out quicksort is it's a natural evolution of merge sort, so I encourage you to look it up. And it's also a very fast sort that is often used in places where performance matters. Now, when I say very fast, I said everything's log linear, right? Well, constants can matter, and the constants for most quicksort implementations are just better. Quicksort is not without its cost, though. Well, it has another benefit. It's in place. This algorithm, as you might have intuited from all the moving around back and forth, you have to make copies of things, which means it takes more memory. Quicksort can work in place, which means it doesn't actually need to copy things. It can just shift things around in the array to be sorted. However, quicksort is not a stable sort. What does that mean? Well, picture you have like a spreadsheet with columns, and you sort first by the first column, and then you sort by the second column. You probably want it, okay, to be sorted by the second column, but within that sort to still be ordered by the order of the first column. If that is true, then what you've done is called a stable sort. So you sort a list of users first by by where how long they've been users, and then by how many times they've actually used the site. And if it keeps both those orders, then it's a stable sort. Quicksort is not stable. So if you did both sorts, the second sort would actually disturb the result of the first sort. So there's situations where you want a stable sort. Merge sort is stable and is very commonly used because of that. In fact, that is part of why it's used in as a default sort in, I believe, the JVM. One other quick aside, this is a technique within algorithms. It's not really a class of algorithms, but it's related to quicksort. Quicksort actually can have a pathologically bad case. Quicksort, like merge sort, looks at things and puts them on other sides of each other based on comparisons, but instead of always splitting directly in the middle like merge sort, it uses something called a pivot. And it turns out that if you are deterministic in how you pick which of your elements to pivot around, then for certain inputs, you'll actually be quadratic. And this is really bad because sorts are supposed to be log linear, and a quadratic sort is just fantastically expensive compared to what you should be getting. Bubble sort, which you've probably already learned about, is quadratic, and there's a reason why it's a fun sort to sort of learn, but it's a joke to actually use it, right? So how can quicksort get around this? Well, you can use what's called randomized quicksort, which is just what it sounds like. It picks that pivot randomly. Again, don't have time to go into all the details, but I'll provide it as a resource for those interested. The intuition that I want to get to you, though, is it's somewhat counterintuitive, but there can be situations where just being random, not actually asking the computer to do something smart, to look at the values and pick the right thing, just being random is best. And quicksort is a case where any other approach where you try to come up with, no, we're going to come up with a rule to pick the right pivot and be good about it. Well, it turns out that just random is actually really cheap, easy, and efficient. It's just the way it's actually done. So with that, we will move on to our next general programming paradigm, which is called dynamic programming. And this is not actually an example of dynamic programming just yet, but we will get there. First, I just want to give a little bit of history about what dynamic programming is and a little bit of general intuition for what it is. It's what's called an optimization technique. And essentially, the intuition is if with greedy approaches, you solve things by having this greedy heuristic. And with divide and conquer, you solve things by dividing into these independent subproblems and then putting them together. With dynamic programming, you remember things cleverly. That's called memoization. You have some data structure to remember information as you solve that. You divide into subproblems, like with divide and conquer, but the subproblems depend on one another. and can be used to solve one another. And this is different from combining a solution to a larger problem. You're more iterating and growing the size of the problem as you go, one by one usually. Now, one fun fact, this kind of sophisticated name, dynamic programming, it's kind of meaningless, or really it's marketing. It was developed at RAND, a research institute, in 1949 by someone named Bellman. And at the time, and still today, RAND gets its money from government, military sort of research grants. And the Secretary of Defense back then was not fond of mathematics and did not like giving money towards mathematical research. And here Bellman was working on something that it was basically math. I mean, yes, it's computer science, but especially in 1949, the distinction between the two when you're working on theory is not crisp. It's math, really. But Bellman needed something to call it other than optimization, math, etc. So he came up with this term, dynamic programming, to sort of reflect the, dynamics is just a good sort of word to reflect how it adapts, and programming because it's, planning and deciding things, and it worked. And, he got the money at the time, and it's still a successful technique today. So before we get to an example of it, let's show essentially a counterexample. Fibonacci numbers. So you're familiar with Fibonacci numbers. Fibonacci numbers are a commonly known sequence of integers that just grow by adding the two previous numbers together to get the next number. And they make this sort of seashell pattern and can be visualized and have all sorts of cool, crazy properties that we're not going to talk about at all. And you can think, well, this, as I was just saying, computer science, math, very similar. And you can write a function to calculate Fibonacci numbers that's pretty much the same as the definition of how to calculate Fibonacci numbers in a mathematical textbook. And it uses recursion, which is essentially what the definition does too, because it refers to itself. It says, okay, we have a special case here. If n is 0, it's 0. We start with 0. If n is 1, it's 1. And if n is anything else, what's the second Fibonacci number? Well, it's the sum of the 0th and the 1th, the first Fibonacci number, and then etc. from there. And this works, right? We can use this to calculate, certainly to work for the base cases. That's no problem at all. And we can say, hey, what's the 5th Fibonacci number? What's the 10th Fibonacci number? And it figures that out. It adds together recursively, figures out what it needs to do. All right, well, what's the problem with this? Remember how I said that, the log of pretty much anything is 30, 40, something like that? Well, if you have an exponential algorithm, it also actually blows up around the same point. If you try to apply an exponential algorithm, okay, 30, it's working. 40, it seems to be thinking a bit, but it made it. What about 50? Can we do 50? This is taking much, much longer than 40 did. In fact, if we wait a moment here, what should happen is the browser ought to complain and say, yes, a web page is slowing you down. What would you like to do? Well, I'm going to go ahead and stop it. Maybe it would terminate eventually, but we're not going to wait to find out. And certainly if I tried 100 or something, that would just not terminate, probably. That would die completely, and it wouldn't work. Okay, but what if we want to know the 100th Fibonacci number? I mean, that should be something a computer can do. Even a human could probably do that if they were patient. So what's the deal? How can we fix this? Well, here's another approach. Now, this is not yet dynamic programming, not really, but it is a step in that direction. It changes the recursion to iterate. And so we're asking what's the nth Fibonacci number? Well, we start by making our array here, and we just hard code, okay, we know that this is the 0th Fibonacci number is 0, the first Fibonacci number is 1, that's just by definition. And now, let's just loop from 2 to n the number we're asking for. And at each step in our loop, we're going to push into our array of Fibonacci numbers the sum of the previous two numbers. So you notice there's no recursive call here. We're just looping, and it's going to be linear because at each step we're just, linear in. For each value, we're just saying, okay, let's add another number to the array, and it's just a simple addition of two numbers that we already have. And then at the end, well, just return the nth Fibonacci number. We actually have all of them, but all we want is the nth. In this case, the base cases, of course, still work. 10 is fine, 30, 40, much faster, 50, 500. You'll notice that at this point, it's actually gotten really big. This is scientific notation. So this is not a precise integer value right now. This is, about 1.4 times 10 to the 104th. So a very large number, but hey, we got it quite quick. We could even go bigger than this. Eventually, we'll get to the biggest number that JavaScript can express, and you can do that on your own if you're curious. For real scientific computing, that JavaScript can express. For real scientific computing, you might want to use a language or package that supports what's called arbitrary precision, which lets you fit in basically as big a number as your computer memory can handle. So that previous example was a step towards dynamic programming. In a sense, this array that we're saving values in is kind of like memorization. But let's go ahead and show that by using something like that, by using a structure to remember previous values, we can even make the recursive approach efficient. We can actually save ourselves from the exponential explosion and still use a recursive structured function for calculating Fibonacci numbers, but by remembering, by using memoization, to have previous values and using them when we have them rather than recalculating them, it still runs fast. So let's talk a little bit about what this code is doing then. It's doing what I just said. Fibs is where we're going to store the previously calculated values, and for convenience, I defined it outside of the function scope. If this was a real program, maybe this whole thing would be inside a class, something like that. And then here's our function that's going to take the n that we want the nth Fibonacci. And we start by saying, hey, do we already know the nth Fibonacci, right? Well, if so, return it. That's what we care about. Okay, that's great. What if we don't? All right, well, then we've got to calculate it. That's what res, the result, is here. And we're still going to calculate it recursively. This looks, an awful lot like this line here of the naive recursive approach. But then, after we calculate it, we're going to push it onto the array, save it that is, and then we're going to return it. Now, how does this then work? Well, because it's recursive, it's going to keep pushing down. If you ask for the 100th Fibonacci number, it'll recurse down to the smaller Fibonacci numbers, just like the recursive solution, and push those first, so they end up there in the right order. And then those will return and feed the solutions to the larger Fibonacci numbers till you eventually get the Fibonacci number that you wanted from the initial call. And that's what you will end up getting actually returned by the overall call to the function. So just to prove that it works, again, base cases are fine, 10 is fine, 100 is fine, 500 is fine, should be the same value, looks like the same value. So that's great. Though I can't inspect it in this particular environment, fibs actually would have all those values now. All the Fibonacci numbers from 0, the 0th one to the 500th would be there saved to look up. Now, you might think, well, there's still two recursive calls here, so why didn't it explode? Well, it didn't explode because it didn't have to recalculate values. It still built the solution recursively, but there wasn't any redundancy. To try to get at this intuition, you can picture this is the recursive call stack if you say ask for the Fibonacci number, the 5th one. And it's going to end up saying, okay, we need the 4th and the 3rd, And when we want the third, we need the second and the first. When we need the second, we need the first and the zeroth. The zeroth and the first are all base cases, so there's no calls below that, and then similarly below the fourth. In the pure recursive version that we initially defined here, every single one of these calls is going to essentially have to do all the work all the way down, recalculate everything. Whereas in this case, in our dynamic programming approach that uses memoization to remember values, we still end up building a similar tree to some extent, but let's say we calculate down this side first. Then when we go down this side, we already find the solution to 3 because we had to calculate it here. So we actually don't go any further down. Or if we'd gone down this side first, then when we go down 4 and when we hit 3 here, hey, we already have 3. So we don't go back down to 2 or 1. And you can picture if instead of 5, this was like 500 or something, it will collapse the tree much more dramatically because you won't have to calculate all of its children exponentially many times. You just sort of have to get the ones that you just pull the value that you already got, basically. So again, memoization is a trick that makes dynamic programming go. There's actually a lot more to dynamic programming that I'm not going to fit in right now. Hopefully we'll get to a little bit later, either in Q&A or assignments. But basically, with memoization, there's lots of trees, and you can take top-down or bottom-up approaches to try to solve problems. But again, the general idea is you have subproblems. The subproblems depend on one another, but you can actually use that dependency to solve them more efficiently if you remember the values as you go. One last note, dynamic programming necessarily, because you're saving data, you're building this data structure, it gives you a sort of space performance trade-off. You're going to use up more space, more of your memory, to hopefully improve your performance. That's often a very good trade to make, but there are some situations where that sort of consideration might actually limit what you can do with dynamic programming. So that's it for the general types of algorithms that I'm going to mention for now. As I said, there's more, but this is a good start. Right now, though, I want to talk about how to think algorithmically. You have these tools. How do you use them? There is no silver bullet. There is no objectively correct answer here, but I want to share some good practices and ways to get started. So the first step when you face a problem is make sure you know and clearly define what the input and output is. I didn't really explicitly do that, but with each of these examples, it was hopefully pretty clear. With Fibonacci numbers, the input is n. I want the nth Fibonacci number. The output is the nth Fibonacci number, both numbers. With sorting, the input is an unsorted list. The output is a sorted list, etc. With the minimum spanning tree, the input is really any graph, and the output is the minimum spanning tree for that. Not any graph, right? An undirected weighted graph. But again, make sure you know what that is, and then ask what data structure is natural for that input and output. Graph, list, I already said these words. You'll probably say those words as you set this up. As you're thinking about these things, you can also start sketching in pseudocode, which is this sort of not actually a programming language, but describe using the same sort of keywords and structures you would write an actual programming language, what these things are and how you would start trying to solve them. I'm not going to go into pseudocode in depth here because there's lots of different schools of thought, and you'll sort of have to build up your own approach with experience. But it's definitely a good practice to at least try to use something like that when you're approaching a new problem. Now, after you've thought about it a bit, you will also want to code up actual working prototypes, not just pseudocode, and you can start trying these tools that we just talked about in your algorithmic toolkit. You're also going to want some test data. Small test data that you make by hand is totally fine, just to test correctness, because if an algorithm isn't correct, you probably don't want to use it. A possible exception to that are what are called approximation algorithms, algorithms that don't give you a solution that's necessarily fully correct, but that's somehow close enough within some confidence. We'll talk about that a little bit more later on, but it's not something you'll need to worry about directly. It's just something that you should be aware of that it exists. So besides small test cases, if possible, try to get at least one test case that's a little bigger. It does not have to be 1,000,000 observations. Just 100 is enough to show that at least what you're doing is probably not exponential, because as I showed you with Fibonacci, that blew up at around n equals 50, right? So if you're able to get enough input that tests that, that's good. And of course, if your input is just a number, really you can put any number you want. If your input's a graph or something, it might be a little more burdensome, but it's still worth, if you're really doing this, to try to make sure you have a test case that shows that your algorithm can actually run at least a decent scale. Once you have all that, you should start by just trying to pick any solution that you think you can put together, just to show that the problem is even solvable, because some problems aren't. Often this first workable solution will be greedy. You will come up with a greedy heuristic like, hey, we want all the smallest things. Why not just pick the smallest thing we can see and keep going? It's basically minimum spanning tree, right? Prim's algorithm for it. So, you can try that and just do it and check if it works, check if it runs efficiently, and if it does, then you might be in a good place. What about if you can think of the problem as bags of smaller independent problems that are similar to each other? Well, you might want to try recursing them and see if a divide and conquer approach works. You'll have to think about an efficient way to combine the solutions of them, but the problems themselves are independent and can just be solved on their own. What if you could think of the problem as a sequence of smaller to large problems, iterating over an array of some sort, and as the problems grow, they're harder, but they can use the solutions from the previous problems? Well, that's the dynamic programming, right? Now, not every problem you face will just sort of naturally fit in one of these, but try to keep your eye out and be creative. Think about the data structures that are involved. And again, there are other techniques we're not covering here. So if you're really interested, you should take some full algorithms classes or get some textbooks or other bigger resources. It's a serious investment of time. And I find it takes repeated exposure for this stuff to stick at all. But it's definitely worth doing, especially if it interests you. So going back to the idea of correctness, basically, you always want to make sure your algorithm is correct. The exception, just to address it, is if you're using a approximation algorithm to solve what's called an NP-complete or a hard problem. So you've probably already heard of traveling salesman. Traveling salesman is this problem that seems simple, almost seems understandable, but actually blows up exponentially no matter what you do if you try to find the true solution. And so at the same time, it's something that real organizations have to solve. UPS and airlines, they have to figure out something that's kind of like traveling salesmen, how to send their resources around efficiently. How do they do it? Well, they hire smart people, and those smart people code an approach that's actually not necessarily the true answer, but it's close enough. It's within a few percent, say, and it can actually be calculated. So there you go. The second goal, besides correctness, or close enough correctness, depending on your case, is efficiency. So you have your working algorithm. Maybe your greedy heuristic worked. Maybe you came up with a clever dynamic programming approach. Whatever you did, now you want to look at it and say, can this be faster? Can I make this better? And one of the main places to look, as was probably made clear with the complexity illustrations here, is anywhere you iterate. First, ask, are there any redundancies? Am I iterating at this place and then iterating again, and I could just iterate the once? And then look especially hard at nested iteration, because that's where you get in these quadratic cases or worse. And ask yourself, do I really need to do this? Could I perhaps save something from an different part of the algorithm and use it to avoid iterating here, sort of almost a minimalization sort of approach maybe. Or maybe don't even actually have to look at all these combinations. I just wrote it as a nested for loop because that was easy, it came naturally, but I don't actually care about everything in this. I only care about some things, and you can find a better way to iterate over them. And another thing with all this talk about iteration, you're likely going to be working mostly with high-level programming languages. JavaScript is definitely one, Python, most popular languages, other than C. And what this means is iteration isn't always explicit. It's not just for loops. A lot of these nice, shiny features you get, the syntactic sugar where you can use some special symbol or some way to express something really succinctly, they might actually iterate. Higher order functions like map and reduce and fold, list comprehensions in Python, all of these things iterate, even though you didn't write the word for a while. And so you might have nested, quadratic, or cubic, or worse iteration in your code if you use these features a lot and don't think about that. So make sure to think about it. And also as a general comment about iteration in high versus low-level languages, it's a little more expensive in high-level languages to iterate because they're doing nice things for you, like checking the bounds to make sure that you're actually iterating over things that exist. In C, a low-level language, iteration is literally just incrementing a pointer, just taking an address in memory and moving it up. And so it's really cheap and really fast and potentially really dangerous. This difference won't matter to you most of the time. It matters for things like math libraries, for really computation-heavy things. And that's why most real math libraries are written in something like C or maybe Fortran. And then you can still access them from, say, Python. There might be a Python library that wraps around it, so you're writing Python code. But when it's actually doing the math, that's probably C. So just something to be aware of. So what else about efficiency? Well, it's not just about for loops and asymptotics. Performance improvements can also have to do with constants. I know earlier I said they don't matter, and that's what Big O says. Big O says ignore the constants. And when you're just initially trying to solve a problem and think about it at a high level, it matters a lot more which of these classes you end up with in terms of overall complexity. But once you're pretty set and have a working solution, depending what you're working on, it might be worth looking at your constants again. Get the working solution first. Never start by optimizing constants, but when you're refining, think about it, because if you're in a situation where you're paying for your compute, you're running something on the cloud, and you can change a constant from 1 to a half, that might cut your compute bill in half, right? And that's a good, or make your thing load twice as fast or be done twice as early or whatever, and that's great. So again, the overall goal when you're doing algorithmic problem solving, define the input-output, think about the data structure, try your tools, and test for correctness, and then think about scalability and efficiency. And that's sort of the overall approach that I'd recommend. You'll learn and apply your own thoughts as you develop in this field, though. So a few other closing comments about algorithms in general, just to motivate your further studies in this area. As I said, algorithms and data structures are connected, so familiarize yourself with what sort of data structures are out there. Wikipedia is a decent resource to at least get a quick overview. You have arrays, which are elements in order addressed by offset. So picking out an element is constant, you just point at it. Searching is linear, you need to look at everything. Editing, inserting and deleting, perhaps somewhat counterintuitively, can be linear because you might have to actually move everything else in order to keep the address and the addressing working. Linked lists, which you've already worked with, in this case, it's just these nodes that have pointers back and forth to them potentially, and there are various variants like stacks and queues, different rules. But essentially the trade-off is finding things is harder. Random access requires even just looking over, same as search. But editing is cheaper. Inserting and deleting is just updating a constant number of pointers, so a fixed cost. There's other things, I'm not going to talk about all of these. I point out, it's not listed here, but a set is an unordered collection of unique elements. It's constant time to check for the existence, the presence of something in a set, and you can think of it as just the keys of a hash table. But it's a very useful data structure for a lot of real-world problems. A lot of things are naturally sets. Hash tables, also very natural because the keys correspond to some value. The user ID returns the overall object for the user, etc. And then there's all sorts of things, trees and graphs, which you can think of as generalizations of lists that can fan out in multiple ways. There's a kind of fancy, well, moderately fancy thing called a red-black tree that can come up in interviews. And these are all real. They're not just interview trivia. Trees are how database engines such as Postgres can build indices, so you can do things efficiently. You can search over all of your data. But the practical takeaway is be aware of what sort of structures exist, and in particular, be aware of the options and the whatever peculiarities or particularities of these options are in whatever language or ecosystem you're working on. So JavaScript, familiarize yourself with the JavaScript objects, and be aware, for instance, that traditional arrays in JavaScript are actually just objects, and they're actually just sort of special objects, kind of, that it's been agreed that the keys are integers that generally go up starting from 0. That sounds like an array, but that's really very different from like a true C array, where those numbers actually correspond to direct memory offsets. They're not keys in a hash table. So that changes if, just say you don't want to write a math library with direct naive JavaScript arrays. Modern JavaScript has typed arrays, which are a little bit more performant and more like a true array from other languages. But the point is these are the sorts of things to be aware of, and to also know what's idiomatic, what's typical to use. If you're writing Python, you should know about dicts, because pretty much all good Python code uses them very heavily. They're basically hash tables, but be familiar with them and be familiar with the specific methods even for them in that environment. So, what's the moral of the story? There's a few other general terms I want to throw out there just so you're aware of them, and also if you're curious, you can ask questions and I'm happy to share more resources. Related to scale and asymptotics is distributed programming. This is a really huge, hard, crazy topic, but it often uses functional programming, which is where you use higher order functions like map and reduce that take functions and execute them at scale, distributed in some fashion, and combine the results. And this is basically what allows us to do big data and what makes a lot of the modern web go. So you should know that much, and if you want to know more, you should look into it, and I'm happy to help. The moral of the story in terms of algorithms, and actually one other sort of buzzword to mention, I guess, actually. Quantum computing is another huge topic. I'll share a link, a talk by Scott Aronson, who's a respected researcher in the field, called What Quantum Computing Isn't. I think this is a good introduction. It isn't, or it isn't what you think. You'll find out. It's exciting. It's not Star Trek, but it is cool. Now, the other aside to mention is Moore's Law. That's probably something else you've heard, and I just want to address it because it comes up in the context of algorithms as well. It's usually translated roughly as everything's getting faster exponentially or something. It's really about the chip-making process. Things get smaller, and so you can put more transistors in an area, and so yes, that means that chips often get faster. This has been going on for some decades. It's actually kind of slowing down due to physics that I can't claim to really understand. They might have to switch to something other than silicon if they want to keep it going. But the important thing to realize is, counter to your intuition, Moore's Law doesn't mean you don't care about big O or efficiency. Moore's Law makes it more important because Moore's Law takes us even farther out here to the right, which makes the gap between a quadratic and log linear even bigger, because with faster, bigger, better computers, we want to solve even bigger problems. And so yeah, it's faster, it's better, and it could solve small quadratic problems or medium quadratic problems, or even large ones if you distribute it and are willing to pay. But you'd really like to be log linear or linear if you want something to just run quickly and run at really big scale. So Moore's law doesn't just give us stuff for free. It actually makes what we would do in algorithms more important. And the other, well, no, I will get to the moral of the story for real now. The moral of the story is that you want to optimize, when you think about algorithms, you want to optimize your time first, and you want to figure out what works and then refine from there. Programmer time usually matters more than computer time. Trying to optimize too much up front, spending too much time planning, trying to get that perfect log linear algorithm with the smallest constants, that might actually just mean that you don't actually get anything out the door, and you don't ship your product, you don't get any money, whatever. So you don't want to prematurely optimize. Asymptotics matter. You want to avoid exponential at all costs, pretty much. But start with something that works, iterate from there, and then figure out the trade-off, the balance that's appropriate for your use case. If your code is going to run a lot at scale, then actually maybe every byte matters. Maybe you do want to really refine it once you get it working. You can launch and iterate for that refinement, but you still want to think about it. If your code is running on a constrained platform, it used to be phones were the example. These days, though, phones are basically locked down desktop computers in your pocket. But let's say you want to run an Arduino or the Internet of Things. You want to write code that runs on people's refrigerators or something. Well, that's a really constrained platform. And so you might actually even care about constants for some things. You might care about the fixed size. You might really care about something, how much memory it takes. So something running in place, like I described earlier with Quicksort, might be really good versus something that has to copy things around because you only have 16 kilobytes of RAM or something. So start with what works and then get more specific as you go. That's the overall moral that I would encourage. And in general, when it comes to these efficiency classes, you'll get a feel for them as you go. Quadratic is tractable, just not cheap to scale. Log linear and linear are cheap, and logarithmic is almost free. Constant is free. You don't want to be on this side, and you'll learn more about that as you go. So anyway, I hope all this was interesting and helpful to you all. We'll be talking more about all these topics. I'll provide these URLs and resources, and we'll be working to actually solve our own problems with algorithms soon. Thank you for watching.